Hello, humanoids and earthlings. Welcome to episode 11, our class on philosophy of climate change. As always, it's Adam with Akbar. And this is a very special episode where we're wrapping up Module 2. And I've given it the audacious, overly ambitious title of What Does It Mean and What Must Be Done? So the idea is hey, can we take all of the things we've learned and try to boil it down to a takeaway message? And so I'm going to try to do that without oversimplifying, with the caveat, of course, there's a whole lot of interpretation and debate about what it does all mean, that is the climate science, and what we should do in light of it. So I'm going to give you one take on all of that I hope is well-grounded. I'm going to jump into, this is a different one. I don't have very many slides because I'm going to spend most of our time over on the internet with Akbar's help. We'll toggle over there. So our objectives today, to wrap up Module 2 with a big picture takeaway about climate science. And my students, I've assigned you this IPCC 1.5 C report, the summary for policymakers. So I think we can also, through this talk, understand that report and put it in some context. So I'm hoping to get both of those things done. How are we going to proceed? Well, I'm going to do this problem orientation that's based on the UNFCCC. I'll talk a bit about their definition of a dangerous anthropogenic interference in the climate system and how that's cashed out or understood in terms of these temperature targets like 1.5 or 2 degrees C above pre-industrial levels. And these temperature targets then come with corresponding carbon budgets, which is a term we talked about last time a little bit. Wrap up by noting that we are way off target if this is what it means to avoid dangerous interference in the climate system. We need massive changes, and that's the challenge. It's almost hard to comprehend the kind of changes that we would need. And then that leads us into Module 3, which is about climate politics and beyond climate policies. What should we do? So that will be kind of the rest of the course. So I have these slides here. In your notes, I have all of this, and it's all with the hyperlinks to take you where I'm going to go in this lecture. But I'm not going to really linger on these slides here in this talk. So I wanted to put them together. You can look either here or in the notes for all the things I'm going to run through. But what I want to do, Akbar, get me the internet here to share with you. Thank you. I'm going to walk through most of those hyperlinks in that document of your notes or in the PowerPoint and just kind of narrate along. And I'll go a little bit quick, I guess, but again, you can replay this and you can consult all of these links on your own. So let me just give it to you in one sort of sweeping narrative, if I can. So we'll start with, problem orientation. You start with a goals statement, and I've adopted the one here from the UNFCCC, the UN Framework Convention on Climate Change, which is the stabilization of greenhouse gas concentrations in the atmosphere at a level that would prevent dangerous anthropogenic interference with the climate system. That's a phrase we'll get to in a bit, but let's just stick with that goal statement. And you know that you have a problem when you have goals and the trends don't align with that goals. So here's the famous Keeling curve, which we have talked about. This is measuring CO2 concentrations in the atmosphere, up and up and up. So that's trend not pointing towards the goal, right? So maybe we don't know what dangerous interference would look like, but we know that we are pushing the limits here as we keep this trajectory going. In some ways, climate change is almost as simple as that in terms of defining the problem, right? Or you can look at CO2 emissions, right? We've seen this graph before. By the way, I'm using a lot of what I call my climate science sense makers, including the IPCC in this talk. This is Our World in Data, which I put in the notes from an earlier talk. They've got great stuff here, and it's very credible and trustworthy. A lot of good people use this information. So I encourage you to check it out. It just puts it very simply. There's our hockey stick curve, right? The Anthropocene. So Why? So that we have a goal statement, trends are not aligned with that goal. What's causing those trends? Well, the way we live ultimately. So I want to get to, there's direct causes, which is greenhouse gas emissions from the energy sector and from the agriculture land use sector, right? We saw this graph in our last lecture. That's a direct cause. All of these things we do, we drive cars, we use electricity, we have industries, we're eating a lot of meat. All of this produces a lot of different greenhouse gases, in particular carbon dioxide, but also methane. But then you can ask, why do we do all that? And who is this we that's doing it, right? You get to these deeper causes, the indirect causes, capitalism, something about our culture that's premised on productivity, consumption, and growth. And we need to, I think, address that, those deeper causes. At least that's what environmental philosophers are always saying. A lot of environmental policy and climate policy folks says, look, we're not going to address those deeper issues. We just need to focus on the emissions problem, right? We're not going to fix the way people live. We can just fix the impacts of their lifestyles. That's a debate we'll get into. But those are ways of thinking of conditioning factors or causes for the trends. Let me jump over to the next tab here. Projections. Well, one way to sum this up is just to say, if you projected out our current climate policies, would we achieve our goal? And the basic answer is no, probably not. You can see here current policies, we're looking at 2.8 to 3.2 degrees C above pre-industrial levels. That, I would say, the consensus in the IPCC community, if I can use that language, that would be seen as dangerous, right? And so we would not have achieved our goal. So we need to even do better than our pledges and targets that we've got. Okay, that's why some people, and look, you know, this is my favorite climate science sense maker, David Roberts. This is a great, depressing, but also kind of uplifting at the end article to read. Some people are saying, look, we're probably not gonna get to this 1.5 C target. Okay, that's something that we will continue to talk about. What we need to do, this is Carbon Brief, again, you know, my favorite, along with David Roberts. What we need to do is rapidly, on a massive scale, decarbonize the economy. This little graphic is showing you, sorry, I'm not totally on centered here, that had we started decarbonizing energy in the economy sooner, we could have made more gradual changes. But every year that goes on and we increase our emissions, to achieve the net zero by 2050 pathway, which is in the IPCC report, it becomes more and more difficult because we have to ramp it down much more quickly, right? I think I might let this run through one more time just so we can see it here. You see those colored lines coming in? This is the pathways to 1.5 C. These are the kinds of massive decarbonization, eliminating greenhouse gas emissions trajectories we would have to hit to stay below that. If we don't drop them within 8 years or so, we're going to use up the carbon budget. Again, so that's a way to think about this target also. The carbon that would lead to, the carbon emissions that would lead to 1.5 degrees C. So that shows you we need to change something, right? And it needs to be big and rapid. Then there's a question. This is from, I haven't mentioned Vaclav Smil yet. Václav Smil, my favorite energy analyst, and he is skeptical that we're going to make this grand energy transition in the kind of timescales we're talking about in a couple or a few decades. You look at the energy transition over a couple of centuries to go from the green is basically wood, a biofueled world. The brown is fossil fuels. That took a long time, 100 years to get to kind of a fossil fueled world. Are we in 20 years or something? Somehow when the energy used by the world, which isn't captured in this chart just shows you percent of a fixed amount of energy here, where our energy consumption globally is growing. So you have to picture that brown, the fossil fuels, is this huge blob. Are we going to somehow radically chop all that brown out and replace it with, you see this little sliver? Wind and solar? Is that what's going to happen? Nuclear, this little bit here. This is a huge challenge. Okay, which is the context for the IPCC report. So I hope that's helpful. This is the world in the scale, the magnitude of the problem they're trying to address in that report that you all looked at. Now, in the Paris Climate Agreement, the target was 2 degrees C. Actually, it was to be significantly under 2 degrees C if we could be. There is a big difference between 1.5 and 2. And this is, I won't skim through this, but this is a site that I provide where you can look at this. This is based on that IPCC report. So this is a nice sense maker site here from the World Resources Institute. So yeah, maybe 1.5C is better than 2, but 2 is better than 2.5, and 2.5 is better than 3, and 3 is better than 3.5. So this is one of the things David Roberts says, is maybe we won't hit 1.5, but if we could hit 1.7, right? Anywhere we can stop is better than going another 0.1 degree up the chain, because it really does make a difference. Okay, so we talked about the problem orientation, and now we're kind of talking about what does dangerous interference mean? And it means, well, some degree of heating in comparison with pre-industrial levels, and we've been talking about 1.5 or 2, and how to think about those. But again, to get to 1.5 or 2, there's a corresponding carbon budget. There's an amount of carbon you can take from the rocks and stick up in the atmosphere to keep you under that temperature target, right? Another way to think of these carbon budgets then is to think about how much of the proven reserves of fossil fuels, to put ourselves in the energy sector, have to stay in the ground. And this graphic does a nice job of saying, look, it looks like our carbon budget again, is depending on what chance you want to hit what temperature target. So if you want to have a 1 in 3 chance of staying below 1.5 degrees, it looks like our carbon budget is 473 gigatons. Well, how much carbon is sitting there under the ground in proved reserves owned by fossil fuel corporations? 2,900 gigatons. So what does that mean? 84% of it has to stay there unburned in the ground. Think about the economics of that in a capitalist global economy. Now that's if, and I didn't put this last time, remember we saw that bucket? I don't think I put it here, but that bucket that's rapidly filling, and that bucket represents our carbon budget. And the traditional way of mitigating emissions that we're talking about here would be at some point we need to cap that bucket. So we've got to stop all of the things we do that's emitting greenhouse gases. But then I mentioned briefly, well, you could also drill a hole in the bucket, metaphorically, the bottom of it, and essentially suck carbon out of the atmosphere. And that has many names for it. I think, what is it? Carbon CDR. I put this in my notes. Hold on a second. What do we call this? Yes, I'm sorry, carbon dioxide removal or negative emissions. BECS is an acronym. You can look that one up, bioengineering, bioenergy and carbon capture and storage technologies. So could we just suck the carbon out of the air? So it's like, can we keep eating our cake, which is emitting all of this carbon, but then just do liposuction? We'll get to this later, but that looks unlikely. The other one we've talked about is geoengineering. Well, maybe we could avoid dangerous anthropogenic interference, not solely by mitigation, so reducing our emissions, or even carbon capture, removing our emissions. Maybe we could, and this is a research team, put sulfates in the stratosphere to reflect some of the solar radiation, so we kind of artificially cool the planet. This is geoengineering. We'll get to that. Okay, so that's on. Here's the problem orientation. Here's how we should understand dangerous interference in our approaches to trying to mitigate the risks of getting to dangerous interference. Now let's just look at towards the end here, the massive scale of the changes we're looking at. This is from Roger Pilkey Jr. He's one of my more controversial climate science sense makers. I just think the analyses he provides are generally top rate. This is one he put in Forbes, and he said, look, To get to that net zero emissions by 2050, which is one way the IPCC formulates this goal, this 1.5C target can be reached if we're at net zero greenhouse gas or carbon dioxide emissions by 2050. He says to do that is the equivalent of adding one nuclear power plant every day for the next 30 years. And by the way, decommissioning the equivalent amount of fossil fuels, right? We're not going to achieve our goal if we just roll out more nuclear or more renewables. Meanwhile, we continue, and they're just added energy atop a fossil fuel base that doesn't go away. We have to decommission the fossil fuel base while we're adding renewables, okay? And right now, most of the renewables we're adding are just kind of getting piled onto a stock of fossil fuel energy sources that's more or less remaining the same. It's even growing a little bit. And that needs to, again, that needs to come down. Look at the shape of that curve. It's got to come down precipitously. That is a major challenge. Another way to put it, this is a measure of carbon intensity. So carbon per unit of GDP. This is something we talked about a little bit, and we'll come back to it. Right now, we're decarbonizing in this metric at a rate of 1.6% annually. And to achieve the goal that the IPCC report talks about, it would have to be 11.3%. That's just a much steeper drop off than what we're doing now. So we're nowhere near. Okay, upshot. Here's the problem. We've got to decarbonize the economy. We're nowhere near doing that now rapidly enough or at scale that we need to be doing it. In fact, this is from BP's World Statistical Review of Energy, which is a great resource. So, you know, BP, yes, private fossil fuel company, it's good to be skeptical. But they provide this report, which is really well regarded and highly respected. And in the sense of just surveying the world of energy, it's fairly neutral. And yeah, in 2019, carbon emissions were still growing. Now, only growing by a little bit. But look, they've got to be dropping by 11%. So we're moving in the opposite direction of where we need to be going. And a direction we need to be going quickly, we're still kind of moving slowly in the other direction. So it's not good news, I would say, overall, where we stand right now. This is from Leah Stokes, one of my climate science sense makers, a new book that she's got coming out. She calls it the narwhal curve. I kind of like that. No, this is a rate of adoption metric here. So how quickly are we introducing renewables, hydro, and nuclear? So these are your carbon-free or carbon-light sources of energy. Well, in some sense, we've been doing those in a great way. That BP report talks about how renewables are the leading new energy resources coming online. So that's good news. But to reach our targets, this narwhal curve, I kind of like that, shows you that actually, despite how great we're doing, it's nowhere near the sort of acceleration of adoption that we need to have going into 2035. So we need a game-changing, like system-defining break with the past, okay? And right now we're kind of more or less just doing incremental things. That's the way I take her narwhal curve. Okay, I'm gonna wrap it up there. This is a picture of Jen Urso. It's going to bring me back to Akbar here. Where are you? You know, I always have to have an Akbar quote at the end of our talk. So, look, as Akbar said, remember that thing Jen Urso said about hope. Okay, so let's not lose hope. We know the challenge is huge, but let us proceed. Okay, on that note, until next time, may the force be with you.